I want you to remember that the goal is not necessarily to obtain an exact or a very good approximation of a continuous PID, but it helps you understand where the expressions are coming from when you understand the goals of the original people who were working with discrete hardware. You'll remember that if we think about our normal analog controller, right? An analog controller relates an error signal to a manipulated variable. This, we have the bias, and we have Kc times E, which is the proportional term. We have 1 over tau I times the integral of the error. And theoretically, we have this tau d times the derivative of the error. Right, so that's the analog time domain PID controller. And if you follow along with the development of discrete controllers in the book in the previous section, not the discrete transform section, but in the section where we're just trying to go from a differential equation to a difference equation. Right, so remember, the difference between a difference equation and a differential equation is really just conceptually the size of the steps that we're taking. For differential equations, we are taking these infinitesimally small steps. And so at some moment in time, if the error did this over time, then in terms of the full analog version of this, then this surface under the curve, right? So that surface under the curve there would be the integral, right? So that would be the integral of E dt. And at any moment in time, let's say at that particular moment in time where we're calculating, that would be the slope of that line, that tangent line would be dE dt. And so that's mechanically, or let's say in the analog domain, that's the kind of picture that we have. We have an error curve changing, we have a nicely continuous area under a nicely continuous curve. And the key to discretization of this, or the way that the discretization works with the formulas that we have in the book, is that we're going to take this integral and we're going to approximate that by the sum of these kind of steps. And this should be quite familiar to you from, let's say, the way that you were taught how integrals work, right? So this is almost like a Riemann sum kind of approximation. So at any moment in time, I have a value for the error, and I can kind of take the value of that error and say I'm going to approximate that integral. Now, don't be too focused on the exact position at which I drew the error. The basic idea is just that we're approximating it by rectangles. We can obviously do this moving either forward or backward, right? So it is also possible to do that approximation using the error at this time and effectively assume that that error had been there for a while. So both of those are possible. They lead to what are known as forward and backward derivative, or forward and backward approximations of this integral. But the basic idea here is that I'm going to go from a place where I'm going from continuous time. So this error is dt, so it takes all of those infinitesimal values of time, and I'm going to go to a discrete time where now I'm going over k, and you can explain this to yourself in a number of different ways. If you are thinking of E as being a function of time, you would use E of t delta t, or k delta t. So that would give you the E at that moment in time. If you're thinking of E being a series of values, you would just say EK. And you'll find that notationally, we will use those notations interchangeably whenever we're trying to refer to, so we'll use a particular notation to accentuate what kind of thing we're trying to do. If we're trying to think about this as a series that we're summing over, so not a series that we're summing over. I must learn how to turn that off. If we're trying to say E, the discrete version of E is a series, then I would just write EK. But if I were actually trying to calculate that, I might be tempted to write E of K delta T. And so this is a position and this is an actual time. And so that's just a little bit of notation. So we will use these interchangeably, and if we do this, if we do the numerics right and you keep all of our ducks in a row correctly, they will work out to be the same number. If we sum over the errors at those particular moments in time, the way we would implement it in a language like Python is to produce a list of E values, and we would sum over that, and we would know what the position of the list is. Right. Now, that sum, obviously we are integrating over a particular moment in time, and so to calculate the areas correctly, we also have to multiply by delta t. And so at this point, I have a good finite difference approximation of the integral. You'll see often in implementation, we'll kind of keep track of that sum. We won't run through all of the history every single time that we step. We'll keep a running total. So we'll just be accumulating the most recent error value into a running total, just from an implementation point of view. So it's usually quite inefficient to say, I'm going to remember the entire version of history for, if you think about a little controller box that we're building, if we're building a box that's supposed to be plugged in and forgotten about, it's unlikely that that box will have an indefinite memory, like a memory that can store all of the values that it's ever seen ever. And so it's also more likely that that box will be calculating an error, updating a running total, and just working with that running total in the implementation. So that's the first challenge that we have, is to approximate the integral. And that's really straightforward. The second challenge that we have is to approximate the derivative. Now, I want to make it clear that this assumes that we are at some current time. So the way that we would read the expression of the analog version is to say, well, we are updating at a particular moment in time. That's the current time. It is inappropriate for us to develop an expression which needs me to know future values of the error in the development. And so for this reason, while mathematically you have done Riemann sums going both ways and done error estimates or derivative estimates using backward differences, forward differences, and central differences in your mathematical courses, we will only use the backward difference approximation when we are building causal devices, because that's the only device, that's the only thing that can calculate at the current time without having to wait for future information to become available. So I'm going to zoom in on this piece here, and I think this kind of idea is already familiar to most of you, that we're going to have 2 points of time at which we will have known error value. We will have the current time, and we will have time minus delta t. So that's if I were using the kind of units of seconds. We would, and that's in your calculus or whatever, you've probably done finite differences this way, where you assume that you had a function of time available, and you would have to put into that function of time a value with units of time. So t and t minus delta t. But in the alternate version of that expression, you would write that as k and k minus n, or k minus 1. And so the current moment in time, we'll just say, given that it is currently time k, the previous value is k minus 1. And so here, we are trying to approximate the derivative at that moment in time, and I'm trying to make sure that it's clear that those are not the same. So this is the finite difference approximation, and the tangent to that curve, so if that's the curve, you can see that the tangent to the curve can be different at that moment in time from that approximation. In general, it will. We're hoping that we're taking small enough steps that that difference is not very big. But obviously, we're not able to perfectly approximate the derivative. And so we're trying to say that if I was using a derivative, right, that would be change in E over change in time. And, or let's say, approximate that by change in T over change in time. Our change in T, well, our change in E is E k minus E and our change in time is delta t. And that has sorted out our approximation of the derivative. Right? Notice that I could have written that. Mathematically, there's nothing stopping me from writing that with a plus 1 notation. So I could have said it's ek plus 1 minus ek, except that at the moment of time where I'm calculating it, I don't know the value of ek plus 1. This is an important distinction because I could do that if I were working offline. If I had some curve and I were just trying to approximate the derivative, it wouldn't matter whether I was going 1 time step forward or 1 time step back, or whether maybe I chose to average the values over 3 or 4 time steps in a derivative filter. Because that control unit has to calculate a new value right now and cannot wait 1 time step to gather new information, it's basically required to use the backward approximation. Now, if you put all of that together, you end up with the approximation of the position form in the book. So you still have your P bar, you still have your KC, you still have your E. I'm going to now kind of indicate that as EK, and this is now PK. And so this assumes that you have an error at that moment in time. You still have your, 1 over tau I, but now you are going to substitute your sum. So I'm just saying K over E, EK, and you have your difference approximation . Right. And so that is the entire position form. That's the basic idea behind the position form PID. And the next step, and so this is problematic in one particular way. It's hard, or let's say it is, we know that there are some problems with saturation of the integral when we implement integral controllers. So this idea of wind-up, where this sum keeps growing even though the controller output has saturated. We have to kind of build into that sum and like pull it back again. Also, we have this kind of degree of freedom where we have to choose a bias for the controller. And so what you can do is you can write out that exact same expression for the previous time step. Right? And so what you'd end up with is P bar plus Kc E, but this E would be K minus 1, right? And you'd have the same sum, but this sum would go to K minus 1. And over here you'd have EK minus 1 minus EK minus 2. Just check me. That should be basically the same expression but written down for the previous time step. Right? Now I can subtract those two expressions from one another in order to obtain an update so that I can find the change in pk. And so I would then say pk minus pk minus 1, and that would be delta p, right? And the nice thing about subtracting these from one another is that the bias goes away, right? So the bias falls away. I don't have a bias anymore. I just now have Kc. I have Ek minus Ek minus 1, which is delta E, right? I have my tau I, and if you think about those sums, the one sum goes all the way to K, and the other sum goes to just before that. And so if I subtract those sums from one another, I'll just get the last error, right? And so I'll end up there with Ek. So notice at this point I have saved myself having to keep a running total, right? Plus, and this is the part that people kind of struggle with, you end up with, if you look at how many of each thing you have, you still have an Ek. Yes, I'm sorry, guys. Of course, same delta T term from the approximation. So if you look closely at what terms you have in this last term, you have Ek over there, right? So you have one Ek. You have minus Ek minus 1 there, but remember you are subtracting this Ek minus 1. So you actually have minus 2 Ek minus 1, right? And then you have this Ek minus 2 term, but that had a minus, and you're subtracting it, so that becomes a plus. And so you end up with the full expression. You have 1 Ek minus 2 Ek minus 1 plus Ek minus 2. And this is now known as the velocity form. Now, you can actually get to this route. I've chosen to just follow exactly the same route that the textbook uses. So to say, well, I've got this for the first, for time step k, I'll write it down for the previous time step, I'll subtract those expressions from one another. That means I get a change in the output. So now I've got a change in the output, and I've got that in terms of previous errors and a change in the error. Another way of thinking about this is I could take this expression that I originally had for the position form PID, and I could actually just multiply or take the derivative of that expression. Now, you can do this in the Laplace domain. It's slightly easier, but you can basically convince yourself that if you were to find dp dt, right, you'd cancel out that p, or that the derivative of the constant would be 0. You'd get kc you'd get dE dt over there, you'd get 1 over tau e, because the derivative of the integral is just the thing itself, and then you'd get a second derivative over here. Right, so if you just did the derivative, if you just say, well, what if I wanted to find the derivative of that position form controller, you'd see a striking resemblance between that and what you are ending up with over here. So each one of those terms has a equivalent approximation. So now we have our EK and we have our, and this you may recognize as a second order or a finite difference approximation of the second derivative. If you did that in your mathematics classes. Now, the most important thing that I want you to understand about this derivation is none of this, the approximation all happens above this line. So this math is all completely exact. There's no approximation there. It is not correct to imagine that a discrete controller or that a velocity form controller is an approximation or any kind of derivative form of a position form controller. It is the same controller expressed differently. I want to make that very clear. Given the same system, given the same error signal, a velocity form controller and a position form controller will calculate identical output values. Unless the only time when they do not do this is if the output were to saturate at any moment in time. And the reason, well, actually, not only that, there's two things that have to happen. The output has to saturate, and I have to know about it. Because if I simply plug these formulas into a program, in other words, if I'm calculating pk by this formula, I will get a certain pk. If I'm calculating pk by writing pk minus 1 on the other side of that equal sign, and just saying, well, pk is equal to the previous pk plus delta pk. Right, so let me maybe just write that out. So if I take all of that together, I could write down an expression that says pk minus 1 plus delta p. If that is the full extent of my program, my controllers will behave identically. Identically, whether or not the output is saturated. What I mean by that is, if I remember the pk minus 1 that my program calculated, and I use that to calculate a new pk, it doesn't matter whether the output saturates or not. I will calculate exactly the same running sum of this integral. Does that make sense? Because I'm doing all exactly the same calculations. And now a lot of you are looking puzzled because but wait a minute, the book says velocity form controllers do not exhibit integral wind-up. This only is true if I read the previous output back from whatever I used to make that output move. I want you to be very clear on this. If I just remember in a Python variable what p of k minus 1 was, the previous time around my loop, and it becomes 100, saturating the output. Right? So here we are now. I've got my Python program. My Python program is outputting p, right? And there's some kind of limit on p. Maybe it's 100. So I start at some value, and in successive calls to my controller function, I'm calculating higher and higher output values. At some point, I start calculating, if I were using a position form, I calculate higher and higher values. If I just do the calculations in Python, I will keep calculating exactly the same values. Why? Because the Python program doesn't know that the output has saturated. There's no way for it to know just by doing the math itself. The Python program only knows what it asked for. It doesn't know what it got. Does that make sense? The anti-wind-up ability of velocity controllers only works if I read the previous value of pk from the device. Or if I apply limits on the controller output within my program and remember the limited value. If I don't do one of those two things, my controllers in velocity form and position form are exactly the same, because the math works out, as you can see, exactly the same. So the real difference comes in with, and actually I feel that the textbook words this, let's say, in a way that is not conducive to optimal understanding of the situation, right? It basically says velocity mode controllers don't have integral windup, and then it shows you a formula which would exhibit integral windup if you just implemented it as it is in the book. Really the difference is that if you look at these two expressions, if you look at the expression for the position form, the missing piece here is there's no place in that form to put the previous output value, even if I knew it. There's no place here where I can say, oh wait, but I remember I asked for the valve to go from 100 to 110 in the previous time step, and the valve told me what to do. Right? It told me I can't go higher than 100. I'm just going to stay here where I'm happy at 100. If I don't know that, or if I don't know some other way, like of updating that P, I can't avoid integral windup. But what that means is, in this form, in this exact form, there's no easy way to make that update. A little bit later in the book, you will also hear that there's a very straightforward way to stop position form controllers from winding up. Simply put an if in your code that says, if the controller output is saturated, stop integrating. Right? That's just as conceptually easy. Just say, well, I detect that output saturation has occurred and stop integrating. Once the integral, or once the output isn't saturated, start integrating. The difference, of course, is that that requires some logic, right? So we have to have kind of an if here that kind of does the integral conditionally. You know, if the output is saturated, do the integral, otherwise don't do the integral, whatever. In the velocity form, it is completely obvious where the previous output value should go. It should go here inside this red box. But the key thing is I should be reading it from the device or using my previous value subjected to limits instead of just whatever the formula spits out. And so if you are encountering some weird results, if you are finding that your controllers are behaving identically, this is the reason why. If you find that your controllers are behaving significantly differently, you have made a coding error. There should be numerically no difference unless you are near the saturation limits. And so I recommend that when you are testing your code, that you test in a couple of different layers. I recommend that you test your controller code first using a completely smooth transfer function like your first order model that you fit onto your TC lab, without even using the TC lab model, which contains noise or anything like that, so that you can verify for yourself very easily that if you make small set point changes, and you can make it small enough so that you don't saturate the heater output, right? Start at 50, make like a 1 degree Celsius set point change. Remember, on your linear model with your linear controller, that will give you exactly the same behavior as if you made a 10 degree Celsius change. The only reason why you want to make bigger changes in the real world is because you want to kind of escape the noise bound. So when things look like this, when they're all beautifully smooth with no noise, you can start with Q at 50 and make a very, very small set point change. So make sure everything is nice and smooth. Make a very small set point change of like 1 degree and see how that bumps up and see whether the controller behaves the way that you expect. That way you've correctly implemented, that way you've checked that you've correctly done your implementation. Also remember, when you're doing this with the smooth model, you can use very small time steps which will allow you to verify that you get exactly the same behavior as the same controller that you approximated continuously. Once you have satisfied yourself that those boundary conditions hold, in other words, that when you do it on a smooth system, under these controlled conditions and the values don't saturate and so on, then you can implement a larger step change which saturates your output, and then you can clearly observe the difference between the position and the velocity form. It's the only way that you can check the difference. There is no other difference. So if you have any discussion that says, well, the velocity form is better at calculating derivatives, or the velocity form does anything differently from the position form other than come away from limits faster, you've made a terrible mistake. That is wrong. And your group, if you're studying a group and that is what they said, that's also wrong. And so you would notice how this works by, so let's say we make a step change like this, and we saturate the controller, right? And even after the controller is saturated, the temperature will still continue to rise, right? But if we're at some kind of high set point, we'll be winding up in that case. And if we then take the set point down, the difference between a position form and a velocity form will be that the velocity form will come away from that limit immediately when the set point goes down, while the position form will continue along and then come down after that. Because it'll be wound up and it'll have to unwind to get down. So that is literally the only difference. And I want to kind of just make sure that everybody understands that this difference, it's not some magical property that just emerges by itself when you take the derivative of a controller, right? You have to actually wire it all up. And you could do that with the position form. Because I think a lot of people when you just read the book, it seems like the velocity form is so clearly superior to the position form that you're almost like angry at me for even teaching you the position form. But in terms of real practicality, there is very little to choose between the two. They achieve exactly the same results, with the one difference that the velocity form makes it slightly easier, only slightly, not like the position form isn't impossible. It only makes it slightly easier to accommodate read back values of the output. That's the big difference. Really straightforwardly, and that's the last thing I'm going to end with this lecture, is I'm just going to show you what the Z transform of this. I'm just going to use this velocity form just for convenience. I'm just going to copy that. I will leave the position form as an exercise for the reader. Actually, that's a worked example in the textbook, so you don't actually. It's not much of an exercise, but like I'm not going to lecture on it. I'm just going to show you how the velocity form works. So this is the expression. This is the expression that we ended up with calculation of the velocity form. And so what we're going to get is, if I Z transform that, I'll end up with PZ, so these terms will go 1 to 1. PZ minus Z to the minus 1 PZ is equal to Kc, and actually we have to remind ourselves now that that delta T was, or delta E was E K minus 1. And so that becomes Ez minus Z to the minus 1 Ez. I'm going to write these terms below one another. I'm running out of space. Plus 1 over tau I Ez delta T plus tau D over delta T. And here are the tough terms. So that's Ez minus 2 E Z to the Z minus 1 plus Ez times Z to the minus 2. Get all the brackets there. Right, so I've successfully Z transformed my difference equation. And you can see it's really, really straightforward. It's not much of a rule, right? It's just like you just multiply by the power of Z, the negative power of Z that is equal to the lag of the how many terms you're going back. And once I have done this with my brain, this is the part that SymPy isn't really great at. SymPy is really great at when I type in that to solve that so that there's only one E left-hand side. And so that effectively gives me a transfer function over there.